Alright, so this problem says an automobile starter motor has an equivalent resistance of 0.05 ohms. So the motor has a resistance of 0.05 ohms and it's supplied by a 12 volt battery with a 0.01 internal resistance. Okay, so here's how this in a circuit it looks like. Here's a circuit diagram. The internal resistance is denoted by little r, and that's the internal resistance. Here is the external resistance, which is called the load. Okay, so the internal resistance is equal to 0.01 ohms and the load is 0.05 ohms. Okay, and the question is part A, what is the current to the motor? Okay. So let's do one part at a time. Now the current in the circuit, okay, is as follows. The total resistance is, these two guys are in series, so the total resistance is this plus that, 0.06 ohms. Okay, and according to Ohm's law, the current in the circuit is the voltage divided by the total resistance, and that's 12 volts divided by 0.05 plus 0.01 ohm. Okay, and so this is 1200 divided by 6, 200 amps. Yeah. So to get your car started, what you need is a current of 200 amps. Okay? As a comparison, your dishwasher and, well, your washing machine probably runs on 10 amps or something like that. So to crank your car up, you need roughly like 20 washing machines. Okay? All right, what voltage is applied to it? Now what they're saying is, so this is your starter motor. What is the voltage that the starter motor is seeing? The voltage that the starter motor is seeing is this, the voltage at this location. Okay, so because the current is flowing, and that is known as the terminal voltage. Okay? And that's what an external load sees. Okay, so we'll call this VA, VB. Okay. So that's outside of the battery. So for instance, if your battery, this is 12 volts, that's the EMF of the battery and that's the maximum voltage it can provide. The motor is not seeing 12 volts. The motor is seeing this voltage. Okay. And so here's how you do this. There's a current flowing like that. Current is flowing in this direction, so you're flowing from a higher to a lower voltage and so on. So let's solve this. Okay, so VB, or here's another way of looking at it. Here's an easier way of looking at it. VA VB is the voltage across this load, and the voltage across this load is just I times this R. Okay, so voltage on across R and the current is 200 amps times 0.05 ohms, and that's 10 volts. So the starter motor is seeing 10 volts, not 12 volts. Okay, and what you have is a 2 volt drop across this thing. Okay. Now let me show you this in a different way as well. Okay. VA minus VB, okay, is also equal to, so we'll use Kirchhoff's rule. This is you're going, current is flowing in this direction. So when you flow with the current, the voltage drop across it is negative. So that's minus IR. And then when you go across this, you get plus 12 volts. Oops. Okay. When you go across this, you are getting plus 12 volts. So VA minus VB is minus IR plus 12 volts. And this should, so minus I is 200 amps, R is 0.01 ohms plus 12 volts, and that's equal to minus 2 volts plus 12 volts equal to 10 volts. So here's another way of showing the terminal voltage, the voltage that the motor is seeing. Okay. All right, let's see what is the next one. What power is supplied to the motor? Yep. So what is the rate at which energy is supplied to the motor? So see, the power supplied to any device is the voltage across that device times the current, or I square R, or V square over R. So you can use any one of those formulas to calculate the power supplied to the device. Okay. So what we'll do is, the device is the motor, 200 amps flow through it, and its resistance is 0.05 ohms. So we'll use that. And this works out to, so that's 10 to the 4, 10 square, 4 times 4, 20,000 watts, 2,000 watts, right? 4, yep. So your starter motor is a 2,000 watt motor. Yep. And then what else? Repeat these calculations when the battery connections are corroded and add 0.09 ohm to the circuit. All right, so now what happens is the following. I'll do just one part. So now here is the internal resistance. Here is your load, which is the motor. And when the battery connections get corroded, what you end up doing is adding in more resistance there. Okay, and that is 0.09 ohms. Okay, so this is why you need to keep your terminals clean. And now the current in the circuit is voltage divided by the total resistance, 12 volts divided by 0.01 plus 0.09 plus 0.05. Okay, and that is equal to 80 amps. Okay, so the current dropped from 200 amps to 80 amps because of corrosion at the terminals. Okay, and the power to the motor is I square R, which is 80 amps squared divided times 0.05, and 320 watts. Okay, so the rate at which energy was supplied to the motor dropped from 2,000 watts to 320 watts. Okay, so that's what corrosions at the terminal did. Okay. All right. So essentially what you're seeing is, okay, if you add a resistance comparable to the load, here's the load, and this resistance because of corrosion is greater than the load, you're changing the behavior of the circuit. Or okay, so this load will not perform as intended.